Okay, everyone. Welcome. So great to see so many of you here, which is great, which means that you're sticking with it. I appreciate that. So to be honest, these few lectures will be, let's say, not the most exciting ones. I'm not proud to say that. I don't want to advertise and say that I will do a bad lecture. I'll try my best not to. However, let's just recap what we want to do. Our goal is to learn how to do great digital circuits. We want to make the best of the best, okay? We want to at least learn what goes into making the best of the best. So this is the goal of the lecture. And what we saw on Friday was we were talking about the EE perspective, where they had like these ugly things which we call transistors. It's not so important. I'll just draw something because, as a kid, I wanted to draw things, and we talked that these are the transistors. And what we should take home was that these transistors can work as switches. We can manufacture them very efficiently. They fall into two categories. There was the PMOS transistors whose job was to work when the output goes up, when the output of our digital circuit switches from 0 to 1. It's this guy doing the work. And when you had an NMOS transistor, his job was to pull things down to a lower level. And we worked with these two levels. We had a level 0, we had a level high, level 1. And we said, if we have only these two things, we can do wondrous things. And then after a while in the lecture, we said, you know what, you can combine these in funny combinations. We didn't go so much into detail of it. And a couple of people were saying, oh my God, is he going to ask this in the exam? Is he? We'll see. Okay. We moved from these into gates. We briefly talked about some gates. We said, hey, this thing is an inverter. When there's a 0, it will be in 1 output. When there's a 1 at the input, it will be a 0 in the output. But we said it's not only that. There are a couple of other gates. We said there's an AND gate, there is an OR gate, there is an XNOR gate, XOR gate, whatever. So there were a number of gates. How does that sound? Are you entertained yet? Yeah, Gladiator. Who has watched Gladiator? Oh my God. Too young, I know. Okay, so what we are going to do now is, so that was just giving us a glimpse. This is not why we are here. We learn, we are not going to look at this thing apart from knowing that there are transistors, they are nice, they have two categories and things like that. They form gates. These gates, for the rest of our lecture, will be available to us. We know what they are. You connect them, they have inputs like A and B, whatever, they have Z, and you can define the relationship between them. There's only so many two input gates. Each one of them has a name, they can do something else. And you say, yeah, yay, that's all what I wanted to know. Now, the interesting thing is, we want to use this knowledge, and we want to actually build things that we care about. Because to be very honest, there are a few people in the world that really care about those things, and I'm guessing you are not one of those, right? You want to build the next processor, or you want to learn how to build the next processor. So now we are going to go into an interesting thing. We want to say, you know what? There's so much research, there's so much mathematicians, so many clever people around. Maybe they could help us systematically, knowing that we can build these things, systematically allow us to combine them in ways that will make sense, so that I can get a function out of it, and that function can do something about it. And the thing that will help us is the Boolean algebra. So the Boolean algebra sets some theorems, some axioms, and you know, I'll be honest, they will sound boring. There'll be some theorems, and then we will start doing things we care about. And when we come and talk about things we care about, remember we had this discussion before. When you make a circuit, what do we care about the most? What do you think we care about? Yes? Money. Excellent. You are my guy. Money. In terms of building integrated circuits, the thing that really costs money is how many of these things you need to manufacture. The more you have, the more functionality you have to pack, the more area you need, and you pay per area. You know, it's like if you need 1 million of those, you pay 1 cent, and if you need 10 million of those, you pay 10 cents. Okay? So money equals the area. What else? Yes? Power. Power? Excellent. Power or energy. And you realize that there is this transistor that pulls things up. There's this transistor that pulls things down. How does he do that? Well, there's somewhere a capacitor, and then there is a current, and that current carries electrons left and right. Now, we don't need to be electrical engineering geeks, but anytime current is flowing left and right, we might be using some power. The more of them we have, the more of them they switch and change their minds. Are you a 1? Are you a 0? Oh, no, I'm a 1. Here, some electrons, charge the capacitor. Okay, I'm a 1. No, I want to be a 0. Okay, electrons go back. So these things actually end up costing power. So the less of them we have, the more efficient we can work. Fortunately, there are some other tricks. We can also say, you know, you can all be here, but you all keep quiet. Don't transfer any electrons. So we are going to talk about that. It's a later story. What else? Yes? Correctness. Very good, correctness, okay. Let's not make circuits that don't work. Now, correctness also will sort of kind of tie into our problems because how many am I designing when I'm making a modern chip? Do you remember? I was talking about M2, for example. Is it 10? Is it 1,000? Is it 100,000? Any? Yeah? A few billion. So if I'm making, look, I remember how I was trying to calculate the hexadecimal things, and I made like 3 mistakes within like 30 seconds. Do you remember that, right? I think it's on video somewhere, so you can rewatch it. It's glorious. So imagine that you're making 20 billion or 10 billion of these guys. There are going to be mistakes, especially if you let Frank design them. So we need things to help us design it. We need some sort of automation. We need some sort of things that can take the difficult jobs and make it easier so we make less mistakes. Because we make less mistakes, the result of the circuit will be a better working circuit. We will see later on, in about 3-4 weeks, that we will spend a lot of our time just making sure that what we design is correct. A lot of effort goes into that. One more thing. Yes? Speed. Yes. You know, you go to MediaMarkt, you're not buying the slowest computer there. And speed is also something we will worry about because, you know, it will matter whether or not when you calculate it, you need to go only through 1 of these, or 2 of these, or 5 of these, or 55 of these. Trying to find ways to make a better solution that realizes the same correct thing is going to be something that bothers us a lot. There might be some of the others. However, all the discussions we are going to make, and they will look very, very simple at the beginning, is so that we can find ways to design with these digital building blocks to realize complex functions so that we have a solution that doesn't cost us much, works fast, doesn't consume so much power, and after all, is correct and does what it is supposed to do. This is our job. This is what we will be doing. So let's start and doing things. This is how it looks like. Every great circuit you can simplify in such a diagram. I like such diagrams because, you know, it makes life so much easy. There's a bunch of inputs, tells you what to do. There is a box inside, and then we get to the outputs. And the logic circuit is composed of whatever happens in between. And we have a functional way of saying, hey, what is happening? How are these inputs transformed? And how do they generate an output? In addition to that, we might have some physical properties. In this case, it's timing. It could have also included power as well, but speed, power describes the delay between inputs changing and outputs responding and things like that. And the key of us building things is actually rooted in the capability of us composing them, trying to build a hierarchy of these blocks so that we can manage complexity. So this is what we were covering in the first lecture. So we say that, hey, this big circuit has elements, in this case, element 1, 2, and 3, that also have their own inputs and outputs, and they are composed and put together in some way. So far boring? The others are fascinated by this. First time, okay. Boy, you will like the rest of the lecture. I mean, if you find this part fascinating, want to see. And now you can realize that if you are building a circuit that is composed of many things, not everything is this input and output. You see there at the top, there is something we call N1, net 1, whatever, some name, that is needed to make a connection which is not available from the outside anymore. So we have some inputs, A, B, C, we have some outputs, Y, Z, and we also have internal nodes. Now, we can count the nodes, and we can actually look at the outputs of every circuit element and the inputs to the entire circuit. So we can say, hey, I have 3 inputs, and I'm looking at the outputs. Well, this output goes directly to the output of the circuit, and this output goes directly out. And E1, well, it's connected internally, so I have an additional node here, N1. Okay, sorry, I forgot the simulation to go with us. Okay. Now, every digital circuit is made out of 2 different types of logic circuits. We are talking about digital circuits. So number 1, are the combinational circuits which we are studying this week. Not possible, combinational. In some textbooks, you will hear combinatorial. It's the same thing. These are great, great circuits. Simple. You know why they are simple? You have a set of inputs. The moment you know what the inputs are, you know what the outputs are. There is no history in these guys. They don't remember anything. Just provide them new inputs every time, like clockwork, you will have their outputs. Now, the other slightly annoying guys are sequential logic. So this is the second, we will start covering them in about 2 weeks. Sequential circuits. The difference between combinational and sequential is not that much. There's a tiny difference, and the tiny difference is the outputs are determined by current values of inputs, just like combinational logic, and all previous inputs. These are like vindicative circuits, right? They remember. They have a memory. Yesterday you told me so. Whereas combinational logic, you know, very easy, very simple. So we are going to start with combinational logic. We are going to spend a lot of time understanding what combinational circuits are. And this week, we are starting from the very start. We know that these gates will be used to make combinational circuits. And then we will build them. We will see how some of these algebra helps us construct them. There are some methods how these can be designed. And once we are done, we will move to sequential logic. We will also see how they are implemented in a high-level description language so that we don't have to do drawings and circuit diagrams like EE people. We'll write code like proper CS people, which is good. And once we have covered this part, we will update them, and we will realize all we have to explain is how can we add memory to them, and this will be the sequential circuits. Once you have this, believe it or not, you can design any and every digital circuit in this world. Any and every. It will be great. There is, like, the entire world of digital circuits will be yours. There is a couple of niche applications, let's say, that do not fall into or cannot be designed the way we are explaining it. Don't worry about those, okay? This thing covers a lot, like 99%. Sorry, there was a question. We are all about them. Like the next few hours, we are just talking about them. You'll see enough of them. You will not want to see many of them for the rest of your life. Okay, motivated? Yeah, let's go, let's do something, right? What is this? Now, very, very simple rules. They start very innocuous, but they become complicated, meaning that I can ask great questions about it. Rules of combinational composition. First of all, every circuit element, every element that makes up the circuit is also combinational. Okay? Every node of the circuit, every wire connection we have, is either designated as an input to the circuit or connects exactly one output terminal of a circuit element. I need to explain that. The circuit, now the third one, contains no cyclic paths. Every path through the circuit visits each circuit node at most once. Also looks a little bit complicated, but it will get easier once we start talking about that. Now let's take a look at this. Now we are thinking whether or not this big block is combinational. Now the first assumption is that E1, E2, E3, if these guys have to be combinational, we have to know it. Somebody has to tell us that, hey, Frank, before you, E1, E2, E3, all combinational, all good. Inside them, we made the same check. So if E1 contains BB1 and CC2 and DD5, whatever, they are also all combinational. It goes on like this. So I know that looking down at this circuit, everything is combinational. Now, yeah, the rest looks okay, right? So this B goes to here and goes to here. The every node of the circuit, so these are the nodes. This one, this one, this one, this one, and this one, and this one. So we have 1, 2, 3, 4, 5, 6 nodes in this circuit. And for every node, it's either an input, so this one, this one, this one. Okay, we covered that. Or connects to exactly one output terminal of a circuit. Now, the ones that we didn't cover is this guy, and this guy. Now, N1 is only connected to the output of E1. Good. This output is connected to the output of E2. It's okay that it connects at the same time to E3 and an output. The important thing is it's only being driven, if you want, by this guy. Now this one, now this is easy, right? I mean, Y is directly coming out of E3. Now, maybe to discuss this a little bit more, let's see some examples. Notice that this would be exactly some type of thing that we would ask in the exam. In the exam, we would also be nasty and we would say, why? Like, are these circuits combinational? If not, explain why. Sounds fair? Okay, let's start. Number one. Who says combinational? Whoa, that's simple. Okay, who says no? No, what a good teacher I am. So this is combinational, okay. Number two. This guy. Who says it's combinational? Wow, people study this. Did you ask ChatGPT? Why not? I mean, someone, yeah? There's a cycle. So the output N5 goes back to N4. This is what we call not combinational. Number 3, combinational. Great. Number 4 is also combinational. Let's say go number 5. What do you say? Yes? Why? It has a cycle, and this time it's not from the same circuit, right? So this is combinational logic, this strange character. So you go through 2, and then you come back and also enter. You know, it's very simple, but this is one of the mistakes that we will be making, unfortunately, when designing hardware. So this guy. Now this gets complicated. Yes?
It's not because N6 connects to
Yes, so the output of I3 and the output of I4 connect to N6. So this N6 is not determined by this, it's determined, or you know, this, you see this, you say, no, I'm not playing this game, this is not combinational. Wow, we learned something. Okay, I told you, right, it's going to go slow, we are going to pick it up. Don't be so upset. Show up tomorrow. I get paid by the number of students here, okay? That's not true. So now we have a combinational logic. We have 3 inputs and 2 outputs. We are actually, when you think about it, we can describe this as a functional specification of the outputs in terms of the inputs. So you can say, hey, this S output is probably a function f of a, b, and c in, and the c out is probably a function, a different function, because it probably does something else, also of the same inputs, a, b, c in, right? So this is what we are after. And any kind of combinational circuit you can see this way. This is like an extremely simple thing, and you might be able to just out of like solving a Sudoku example, right? You might look at it and say, yeah, if I do this, I do this. You think about these individual stuff, maybe doodle on your, they are really enjoying the class. You can doodle on your paper and look at it and come up with a solution. But what we are interested in is, if there are these equations and these formulas, is there a way where we can use and construct these equations? Can we, given any function, given any description, can I map it to an algebra? And the algebra allows us to calculate, right? So it's calculation. If I can calculate it, I can manipulate it. Why do I want to manipulate it? Well, because by manipulating this, maybe I can reduce the area, I can increase the speed, I can reduce the power, I can, while still maintaining the correctness. Why shall I use 50 gates when I could do exactly the same thing in 5 gates? Now, the question is, how can I, given a strange description, figure out what is the correct equation to do it? And maybe there's a simple way to get the equation, which is simple to get, but a little bit complex. Maybe if I spend a little bit of time, that equation can reduce and become something more manageable. And that more manageable has some advantages for us. So the good news is, while we were doing this for years, people had discovered the Boolean algebra. They had these 2 values. So Boolean means we have 2 values, and said, hey, here's an entire algebra that relies on us having access to only 2 values. So they have developed it and says, hey, we have to have some axioms. And once I have the axiom, I can have some theorems, then I can prove the theorems. And I can use these all to manipulate Boolean equations. Now, you will see that we will discuss about a number of these, and they have a duality principle. And it's quite cool. We can, any theorem and any axiom will stay correct. We will use some ands, and if we replace the ands by ors, and if we do this, we can exchange the 0 and 1, the entire theorem will still hold. So you define one theorem, let's say with ands, and you get the other one for free. Like, how great is that? No? Yes?
So do we interchange the input values?
Let's do an example, right? So there is this 0 negated, right? Is 1, and B naught is 0, right? So this is something that comes out of it. Now the dual of it is I'll exchange 1s with 0. So 1 negated will be 0. Or I can exchange, in this case, this notation, this would correspond to AND. I say I replace the AND with an OR, and I replace the zeros with a 1. So if B and not B, this will mean that, is 0, B or not B will be 1. Yeah, exactly. Magic. So in a few minutes, we'll be going through them, and we will always realize that there's a dual. Once I define one, the next one will become also obvious. Yes?
Do we keep the negation the same, or do we also have to flip the negation?
No, it's just like that. I mean, ands and ors are interchanged, and zeros and ones are interchanged. The negations stay there. You see it here, right? The first guy didn't have a negation. The second guy did. I kept them as it is. I flipped this, and I flipped this. It's just like a simple trick. Of course, we can prove this formally. That's a different story. Great questions. Shall we take a look at the axioms? Yeah, let's do some maths. Okay. So, the first one, okay, you have to start somewhere, right? B is 0 if B is not 1, meaning that I have two values. Okay? And the dual of it is B is 1 if B is not 0. So it says I have a binary field. My field of the mathematical region that I'm working on only contains zeros and ones. Painfully obvious? Not so much? Okay. So, negation, the inversion. So the negative of, the inversion of 0 is 1. And the obvious is the inversion of 1 is 0. So that defines me an operation. I call this the not operation, the negation. So this is how I specify it. If I draw a bar over it, I mean that this value is negated. In this case, I have a constant which gives us later on, when we go to the theorems, we'll be inverting numbers. Now, the second one is the description of and or. We say 0 and 0 equals to 0. Okay. 0 and 0 makes 0. 1 or 1 equals to 1. That's the dual of it. Boring. Okay. The second part is 1 and 1 equals to 1, and 0 or 0 equals to 0. We're just defining some operations that we can work with. Okay? And then, we covered most of it, but the other one is 0 and 1 is the same as 1 and 0, and they both equal to 0. Or you can say 1 plus 1 or 0, or 0 or 1 equals to 1. Now, we have defined 3 operations, and, or, negation. We have defined 2 values, and that will cover us a number of funny theorems. Why are we doing these theorems? Because at some point, we want to be able to use those gates to make awesome circuits. Believe it or not, this is going to help. Okay? I know it doesn't look very great. So for those of you, this is like the latest invention in educational technology. It might even, doesn't work. Used to, oh, it is. Yeah, I know. There's nothing special. We'll see the same slide there. It's just that the slide will not disappear. Okay. So now we will go through a number of theorems. This guy needs heating up. I see it's slowly coming there. Wondrous example, yeah. Oh my God, yeah. It's not so important. It's the same slide that you see. I just need to point to it from time to time. Okay. The first theorem is identity theorem. So we have an identity operation for both and. I'll just turn it off if you keep on so much. Okay, we have an identity operation for and we have an identity operation for or, meaning that the identity operation doesn't change the value, right? So if you AND some variable with 1, you are going to get the same variable back. Now, there is a direct dual of these things. This is an AND gate. This is an OR gate. To make life a little bit simpler, people that cannot draw very well, sometimes, like me, we also add the operation inside because you see, so this is the AND. And the OR one has like this slight curvature here. And then it has a different type of curvature here. And then goes out and then makes this. So this is the AND guy. And this is the OR guy. Now, if your handwriting or your drawing skills are as bad as mine, a simple trick that we use is we put a dot into this guy and we put a plus into this guy. And when we are drawing it, we sometimes draw it quickly like this. Okay? Yes?
Are we allowed to use the European ones, like the squares with the ampersand and the...
Don't say European ones. Those are the German ones. And no, we are not. I mean, you're allowed to use it, of course. No police is going to come. Please don't use them. For full disclosure, I have a German passport. I can say bad things about the Germans. Okay. Sorry. It's okay. I mean, please don't use them. They are really confusing. I don't know what happened there. At some, I tend to ignore that they exist as a German person. Are you already reporting me to the Schulleitung? No. Okay. So the identity theorem tells us that if I AND some variable with 1, I'm going to get B. If I OR something with B, I'm going to get B. Why is this very interesting? This, in some cases, will allow us to simplify things. Because if I see that there is an AND with 1, I don't need to do that operation. I don't need that gate. That gate is superfluous. Now, there is the other part is a null element. A null element means that it's just the opposite. If I AND something with a B, there is no need to an operation. The output will be 0. Or if I OR something with 1, I don't need the gate. The output will be 1. It doesn't matter because B can be only 0 and 1. And, you know, 0 and 1 is 1. 0 or 1 is 1. And 1 or 1 is 1. So I don't care what B is. The result is always 1. Moving forward, idempotency, B and B. Great company name, no? B and B is B, B or B is B. So if you are operating on the same value twice, you are going to get the same. Involution, if you take a value, invert it, and then invert it again, you are going to get the same. Okay, now the completeness, there can be only 2 values. So if you are ANDing B and not B, you are going to get 0. If you are ORing B or not B, you are going to get 1. Now, both of these, 5 of these things actually help us simplify things because we might see that some of these things might not be needed. Now, let me see here. Yeah, it's horrible. Technology. So this is a summary of the entire thing. Now we can have Boolean theorems. We can expand them to several variables. And then things get a little bit more complicated. We go up to theorem 12. I'm not going to talk so much about it, But, you know, the first one is commutativity, commutativity. B and C is the same as C and B. And then associativity, that is actually very interesting. B and C and D is B and C and D, so you can move them around in the parentheses, right? Yeah, good. Then we have the covering, we have different ones, and then there is this last one, we are going to come to that, which is a quite fun one. This says, if you have B0 and B1 and B2 negated, you can turn this into not B0 or not B1 or not B2. It seems very obscure, I agree. It's very useful. And I'm going to show you, especially in the second hour, a little bit why, and there is a fun, gamey way of how to look at these things. Now, before we go to a break, let us try to put them into action. Oh, yeah, there's not enough room, right? I need to also put these guys there. Now, the axioms we don't need so much. Actually, we need the theorems. You can see them perfectly, right? Mohammad? Clear. I'll pretend that I'm fixing things, okay? It's better, so much better. Okay, so now let's try to make this work. Here's a very simple example. We have some operation which is y equals to not AB or A and B. Now, before we go any further, why I do these things is I realize that if I'm able to reduce this by area, I can reduce this by speed, by power, I have a gain. I'm not trying to change the function. I'm just trying to see, can I be smarter than the next guy? Because I want to get paid more than the next guy, okay? And this is what should interest you. Not everything is money, but you know, it's good to have job security. So you can immediately go and check some of the theorems and say, there's B on both parts, so I can put this into B parentheses, which happens to be T8, which you can clearly see is this guy here, distributivity. Hey, I mean, you're just sitting in front of it, come on. Okay. That made life a little bit easier. And now you look at it, we have it in the B parentheses, not A plus A. You say, hey, I heard this somewhere. And you can say, if I take the T5, that was this guy, right? The completeness, B and not B, it's 1. And, B and 1 is just B. So instead of spending a lot of time trying to calculate what Y is, I could just assign Y to B. I saved a lot of effort because of these wishy-washy theorems. No? Just for the record, this is exactly what will happen. I mean, we will ask you something like that in the exam and say, hey, simplify this equation, yada, yada, yada. So because we like it so much, I'm really curious what they are on to, I mean, it seems to be so interesting, certainly more interesting than this thing. You'll tell me in the break, right? Okay, great. I'm really always like, what is it? Okay, here's a more complex one. Let's go one by one. And there is no art to it. I mean, if you've done any maths course, you've also seen how your teachers come and show you a complex equation, and all of a sudden you see, if I take this into parentheses, everything seems to work magically. Here we have taken both sides into the AB parentheses, theorem 8 again. We see 1 plus C. We realize that guy will disappear. That's 1. And then I have A and B. Well, I'm not going to do 2 A and B's, right? Like A and A is A, so it's just 1 A and B. And voila, instead of writing that funny equation, I could have just written AB, which I think is so much cooler. Well, it's so much cooler because I need to do less work. I need to spend less money making it. It will probably be faster because instead of calculating this A and B and C, or A and B, and then, you know, all these together, and then AND it again. There's a lot of things happening. Instead of it, I will just say, this is A and B. I just realized that this is A and B. Now, De Morgan's theorem is funny. I really like it. It's a kind of a game. A and B not equals to not A or not B. You can prove it. And with two variables, it's very easy. There are only 4 possible solutions, right? You can just write down. You can write A0, B0, A0, B1, A1, B0, A1, B1, and write the output of both circuits, both sides, and you can definitively prove that this thing holds true. And the dual of it is A or B not equals to not A, not B. Now, the fun part here is, this is what happens. If you have a NAND gate, an AND gate with a bubble at the end, that's your NAND, you can, this is equivalent as having an OR gate with 2 bubbles at the beginning. Or if you have a NOR gate with an OR gate followed by an inversion, the bubble here, this equals to an AND gate with 2 bubbles at the beginning. Now this is a very visual kind of theorem. And there are these bubbles, these inversions, and you can push the bubbles around. I like it, it's super cool. You have this bubble, you can push the bubble back to the inputs, and those guys get inverted. The only thing you have to remember is anytime the bubble is pushed back, whatever is AND becomes OR, whatever is OR becomes AND. What a waste of time, you say? And you can go the other way as well. You can push the bubbles this way, so these 2 bubbles disappear and you make this. Notice that bubbles at some point will require you to do some operations. So if you look at it, there is A and B not, C and D not, and both of them are then ANDed and then inverted again. And that looks like a complex operation. If you were to write down, so this part is A and B not, so this is this part. This part is C and D not, so C and D not. And then the 2 of them are ANDed, and then once again, inverted. My God. Now, we can show that. We will show that by using De Morgan theorems. This is actually A and B or C and D, which is such a nicer way of saying it instead of all these inversions here and there. No? No. Okay. There are some funny bubble pushing rules. I think I asked this once in an exam and it wasn't very popular. I'm not very sure if I'm going to do it again. It seems that online there was a description of how this thing gets done, and it was much more complicated than I thought it would be. And everybody studied it from there and didn't make it, I don't know. So the idea is you can start from the beginning and push backwards so that you can try to eliminate as much as possible, and you stop at a point where it doesn't make any sense. So at the moment, this is this kind of function, which looks quite scary. A or B not, and then not C not, and then not D and not. Oh my God. And you can start pushing it. Here's the thing. So we've pushed the first thing, the bubbles appeared here. Now we have 2 bubbles. This is I inverted and then inverted again. And you say, hey, double inversion, no inversion. Great. So the bubbles canceled. And now I also push these guys back. And I also change these things, and I have a different circuit. And now I can go down and write, hey, you know what? This entire thing that looks so much complicated is not A and not B and C or not D. Now, when you look at it, the number of even the characters that you are writing on your exam sheet, right? This thing is much less. And if it is much less, we are also doing less work. And you know, instead of writing this long thing, we can write this thing. If you write this thing, we make less mistakes when we are calculating. We will pay less for the area. Probably, hopefully, it will also maybe work faster, and we might even use less power. So this is why these things are great. Now, to wrap up this lecture. Am I over? No, I'm not over. Excellent. Last slide. Hey, look at the timing. What have we learned? We have learned what we talk about when we say combinational circuit discipline. Yes, I know, sorry. Boolean, we talked about Boolean algebra theorems. Those are those horrible things there. And we briefly talked about bubble pushing because it will come in very handy. It's a nice thing to remember. All these examples and slides are actually from the book. And now it's time for a break, and then we continue.
Can I ask a question about that?
Okay, okay, we're back again. It's okay? Okay, good. This side also okay? Great. Man, I'm so curious about that. Okay, now we are, our goal is to design these circuits, and we are making our way slowly but very surely. Now we talked about the theory. We have this Boolean algebra, we have the theorems, we have the axioms. We know we have ands, ors, negations, something, something. And we talked that we can simplify it. Our goal is still to come up with larger circuits that are made in combinations with these gates. But we don't want to do them manually. We want to have a functionality in our head and have some structured way of designing and working with them. So the first thing is, hey, how can I convert the desired functionality into Boolean equations? I don't want to be like thinking about it, like, I can put an AND gate here and then I'll take the output, invert it. No, I want to, think about the problem, logically formulate it, maybe have a truth table, and out of the truth table, once I have that, I don't want to do too much creativity. I want to make this mundane. Why would I want that? Why don't I want so much creativity in this process? Anyone? No one? Ah, yeah.
Because if we have a formula for it, then we can automate it and automatically resolve.
So excellent answer, right? So if we can break down this annoying and big complex task, which you will see, I mean, it's quite tricky and annoying and also not very motivating. If we can have this task in simple forms that we can describe, we can have some algorithm do it for us. And it doesn't have to be like an AI algorithm that has to learn. No, it can be something that is closed form for which we know there are solutions and it can do it. You can, if you can express it as a linear algebra problem, you can do it. It's great. So I don't have to deal with it. Now, part of this lecture, we are going to, this is not going to finish today, so we are also going to continue tomorrow these slide sets. Part of this is so that we understand what is going on in the background. We will not be designing circuits by the second method, Karnaugh maps, which is like, again, a sort of hands-on way of how to do some optimizations. We want to just understand what's behind it. We want to little bit be involved in what is happening. And then we will talk about circuits with more than one output, and then we are going to talk about timing, and oh my God, timing will be an issue. So now let's start for this, for a very, very simple circuit, a world-breaking circuit. I keep this from the book. People ask me for additional reading. The first few weeks, we are going to stick to the book as much as possible. Anytime, you will see that all these examples actually come and are described in the book. And you'll find it, I hope you'll find it easier to follow. Later on, once we are going into more advanced topics, once we are talking inside of processors, for example, we'll be having additional reading. Now, this is a very, very important circuit. We sit down and we decided that we have to make a circuit to decide this. My choice is, I want to determine whether or not I'm eating lunch. Who had lunch today? Okay, you all had this great circuit and you all decided you want to eat. But me, I have these problems. I'm not going to eat lunch if it's not open or if they only serve cabbage. Now there are three things. One of them is the output, which is, am I eating? And there are two conditions. Is this guy open? And is there only cabbage? I have no idea why cabbage, okay? Don't come to me. Okay, now, as stupid as this sounds, what we can do is, there are only four conditions here, right? It's either open or closed. There's either only cabbage or there is something else. And based on all these four conditions, it's not rocket science. We can just fill them in. Here, it's not open, I'm not eating. It's not open, I'm not eating. I don't care if there's cabbage. It's not open, guys, I'm not eating, okay? And if it's open, I have to see, is there only cabbage? No. Then I'm eating. If there's only cabbage, no, I'm not eating. Okay, sorry. Yeah, I'm not eating. My God, how complicated life can be. So this is, it sounds very, I mean, it's not like what we want to do, right? Like NVIDIA GPUs and things like that doesn't really look like this. However, this is able to demonstrate us how we can come from a textual description. Remember, we started from what we think this is about, and then we moved to a truth table that maybe will help us do more. And to do more, we need some definitions. So first of all, let's start with the first one. We already saw this. If a variable, an input, A, B, C, we will call it a complement if it's a variable with a bar over it. And literals are variables or their complement. So if I have inputs A, B, and C, I know that A and not A, B and not B, C and not B, C are all literals that I can use. Now, an implicant is a product, an AND of literals. So any of these three are literals. Some of them are larger, you know, that has all three of them is A, B, and C. And some of them only have A and C, some of them have B and C. I mean, you can come up with many different literals. Okay? Now, what is interesting are the following. There is min terms, and min terms are products, meaning ANDs, that includes all input variables. And they can be either themselves or their inverse. So a min term with three variables is A, B, and C in various inversions and negations that we have. Okay? It's just a definition. I mean, you know, please don't disagree with definitions. And a max term, so min term is the ANDs, and max term is the sum ORs that include all input variables. Yes?
Is there a specific definition for product of literals, but not for sum of literals?
Good question. No idea. There is probably, I just forgot to put it there. And you'll see that we will not talk too much about these min terms, max terms. On the other hand, we will talk. So min terms are implicants with all terms. He caught me there. Okay, now, here's the interesting thing. Why is it interesting? Given any truth table, we can define any logic function in what we call sum of products or SOP form. So if you have some truth table like this, how do I come up with a function, the output function y, as a function of A and B? And we say, hey, this is easy. All Boolean equations, everything you can imagine can be written in sum of products form. Each row in a truth table has a min term. There are 4 min terms here. A and B, not A and not B, not A and B, A and not B, A and B. There are 4 min terms. And not all the min terms result in a true output, right? You see 2 of those outputs are 1, and 2 of those min terms are 0. So let me just repeat this. So now I had to, no, I want to keep this, can I write it here? Yeah, okay. Sorry, I had to take some directions. So let's write this again. A, B, Y. Takes a lot of courage to go to the blackboard and write zeros and ones where I knew that I made a mistake the last time. You can just use my insecurity and say, ah, mistake. Okay. Is it visible, the last row? But this part they don't see. It's the same as this. Okay. I have to, okay, I'll do this. But they don't see the rest then. Our online viewers, I'm not doing something strange. I'm working on this thing, okay? Don't worry. My God. Okay. Okay. So there are, I'm looking for a nice color. They stole all the nice colors. I have purple. Okay. So there are 4 min terms here, right? So this is not A. This is not A and B. And this is A and not B. And this is A and B. Now, when I want to write down the equation, I can just simply look at the lines that produce a positive output. This one. And we say, hey, when I see in the truth table that if this min term activates, the result is true. So let's take this guy. And then which one else? What is the next guy? This one. Huh. And I say, okay, I had one. Now let's add the second one. Ta-da! That's my Boolean equation for this thing. Let's just advance and see that if we have made it properly. I'm very curious. Yes, Frank. Good. So the board now reflects the same thing as we have. We have 4 different cases. Only 2 of them resulted a positive thing. So you can write the Boolean equation given any truth table directly by ORing the min terms for which the output is true. Any truth table. The only thing that the difficulty now is to make the truth table. And given any kind of thing, you can do this. Now, okay, I'll try this. I'll mute it. And I'm going to this blackboard. Oh, it works. Okay. So let's have a truth table. And let's write them 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1. Ta-da! And I can actually quite randomly write whatever I want. For example, I can say, I want to see when at least 2 of them are 1. Right? So that's my funny function. And say, no, here they are not, here they are not, here they are not, here it is, here it's not, and here it is, here it is, here it is. Right? Whatever. I mean, that was my function. I looked at it. I said, hey, there are 3 inputs. I want to have a 1 at the output when 2 of those guys are 1. And now all I have to do is figure out which lines are true and just write and OR these min terms together. So Z equals to, can somebody say this? Please? Not A, B, C, or this guy. Sorry, it's too far for you. Yeah. A not B, C plus this guy.
A, B, not C.
And the last one is, that's easy. Let me do that, A, B, C. Okay? Notice that I'm not even interested what the function is. As soon as I know, just by, I have a truth table, I can immediately do this thing. Now, here's an interesting question. You also see this one. This should be a little bit familiar. Is this the most efficient way of doing it? Can I simplify it? I could simplify it. How do you know it was just B? Because we already saw this guy.
No, when I checked B and 1,
Okay, that's also a good one. Manual checking. However, given this to an algorithm, he could play with those theorems and also figure out this is his thing. Now, the good news, and this is why we were talking about it the last lecture. Remember, I was showing you, oh, the speed, the thing, and things. Sum of products will give you definitively the solution. It's not going to give you the best solution. Why? Because he is actually taking all the literals. He's forming sums of mean terms, which says that, okay, I'm just counting them in. Now, is this the only way of doing it? We know that there is this duality principle. Well, if there's a duality principle, there is also the product of sums form, which is, I'm not going to do this, but you are going to pick the other guys. And now the trick is, we are going to pick the max terms, not mean terms, the max terms where the output is 0, and add them together. So the same function, notice that it's the same function. I can also write this as A or B, and not A or B. So what I forgot to tell you is we are also inverting the thing. So each max term is false for that row and only that row, and formed by adding the max terms for which the output is 0. So the max terms here is A or B, and not A or B, and then we can have this as a result. Now, the question is, I have two different options. Which one do I choose? Because both of them will give me the same function. I can move from one, I can move to the other one. Which is the best one? And it has actually a very simple solution. You have to take a look at the number of mean terms and max terms that are 0 or 1. In this case, I have only 1 out of 4 outputs that is 1. And since for sum of products, I'm going to add everything that is 1, there's only 1 of them, which means that my job is easier. Whereas here, ta-da, or no. Okay, look at this. Na, 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 na. And we know that by manipulating Boolean theorems, it should be possible to go from this one to that one. I mean, that's a given, because we are not making this thing up. This comes out of the theory. Now, so SOP is shorter if the output is true in only a few cases, and product of sums is shorter if the output is false in only a few cases. In this case, it's easy. If it's 50-50, well, pick whatever you like. You know, you might be more of a sum of products kind of person, or you might be more of a sum of product of sums kind of person. Any questions so far? Somebody seriously took a selfie in the class. Why don't you come here? No, why don't you come here and take a selfie with the entire class behind you? I mean, what? Yeah, go. Here. Come here. Okay. Thanks, I never thought I would see or say, but okay. Okay. So the fun part that you have seen is that you can generate them and you can move between them, but it's not always very obvious how you can move between, I mean, which one is the best way to do it, right? I mean, what's my goal? This is better for everything. This is better for me not making too many mistakes. This uses less power, this has less area, and I think this is faster. I mean, we can argue about it. This looks much more complicated. They do exactly the same thing. So this is where optimizations and why we care comes into play. If you are not if you're too rich, you don't care about these things and says, my time is too precious. It does the job. What do I care? You can leave it at that, obviously. But for those people who need to work for their jobs, we need to maybe figure out how we can do things better. Now, we have, back in the day, like at my time, we didn't have so many computers, no ChatGPT, no selfies, and we had to do these things manually. So we had a truth table, very similar to this one, although it is more on the simpler side here. And there was a way how we could do these minimizations. You know, we can do the parentheses, we could simplify it, and we could write faster things. And it's a bit like Sudoku solving, or, you know, those, what is it, tic-tac-toe kind of games. So it has a funny game type of appeal. This is why it is used in classes quite a lot. Now, let's be very honest. Modern circuits are not done by people sitting down and writing or making these K-maps or Karnaugh maps, okay? Let's be very serious about it. It's not happening. However, it helps us understand how tools can actually simplify this. So now what we are doing here is I'll redraw this. The entire thing will be on the board. So for those who are listening to this in July, you're not missing anything. So okay. So what is the function? This goes 1, 1, 0, 0, 0, 0, 0, 0. And now what we do is I have actually 3 variables, and that means 2 to the 3. I have 8 different sections. So what I do is I draw this funny box. There's a tricky part to it, so be careful here. I assign the variables. I can assign them any way I want. I'll just keep the same thing. I have A and B to the top. And I have C on this part. So C can be either 0 or it can be 1. Okay? So this is the part where the C is 0. They will end up here. And this is the part where C is 1. They will end up here. Now, A and B, how many different options do I have? 4. What are they? Let's start with 0, 0. And now I'm going to write all 4 combinations in here. But while I do this, I'm going to make one very important trick. I'm only going to change one of them at every step. So here it's 0, 0. The next one, I'm going to make 0, 1, which is completely okay. Now the third one is where you make all the mistakes. The third one is not going to be 1, 0. Why? Because I would be changing both this guy and this guy. I will make the third one 1, 1, and the fourth one 1, 0. So moving from this column to this column, only 1 bit changed. Moving from this column to this column, only this guy changed. And moving from here to here, it changed. So this is the tricky part. Okay? We are going to solve one more, don't worry. But the tricky part is here. And now I'm going to fill in these guys. And now the fun starts, or what Frank calls fun. We will try to circle as many friends as we can. Friends are the ones that are next to each other. And we say, each one of them is a min term. Okay? What I want to do is capture as many min terms as I can. Okay? In this case, I captured this thing. And now I want to see which logic function this corresponds to. Notice that this column is where not A, not B is. And you're looking, it doesn't matter the value of C. C can be 0, C can be 1. So I have actually eliminated this guy, and I will say, hey, the output here is yay. Yoo-hoo. No? Okay, here are the rules once again. Karnaugh map rules. This is working, yeah. Special order for bit combinations, so 0, 0, 0, 1, 1, 1, 1, 0. If you really want to be a rebel, any rebels here? There are rebels on that side. You can also go 0, 0, 1, 0, 1, 1, 0, 1, okay? Doesn't matter. It's just the only one bit changes from one to the next. That's the thing. Everyone in this map needs to be circled at least once. Each circle must span a power of 2, 1, 2, 4 squares in each direction. Each circle must be as large as possible. A circle may wrap around the edges of the K-map. Oh my God. And a don't care is circuit only if it helps. Okay, let's leave the last ones here. And let's try to make an example on the blackboard. Oh my God. Oh, this is with X's. Okay, let's make one without the X's. It says blackboard, so I'm pressing the magic button. Okay. And since I'm lazy, I'll just delete these guys. And now I'm going to do something that you should never do in class. Never.
I'll be right back.
Don't worry. No, he won't. Dude is gone. Okay. My God, I won't survive this. Okay, here's the thing. I need your input for making the K-map. So, somebody has to say 0 and 1. Let's start. 1.
0.
No, I don't like that. Okay, it's okay. One more. Let's say 0, 0, 1, 1. Difficult. Difficult with Boolean logic. Now, here is the fun part. So this is the 0, 0, guys, right? So I have when C is 1, when C is 0, I have here 1, I have a 0. So I have covered this part. Now let's go to this thing. When A is 0 and B is 1, A is 0, B is 1, I have 1, 1. Okay. Now when A is 1 and B is 0, no, here. Okay, that's the important bit. A is 1, B is 0. A is 1, B is 0. 0, 1. And then A is 1, B is 1. What? 2, 0. Sorry. Look, come on, happens. I should have like an error counter. Today is like 1, okay? If I make 3 mistakes, you can leave. Everybody's hoping for it now. And now comes the other one. This one. 1, 1. Bad example. Okay. Let's try to circle them. Now you see that there is this nice giant circle. Do you see this? This guy, this guy, this guy, this guy. I can make like this, whoa, yoo-hoo. And when I write the output, Y, what is this? You see that A can be 0 and 1, C can be 0 and 1. And this is true when there is only B. Huh, great. B plus this guy. I can write it like this. Okay. Make sense? And then this would be not A, not B, not C. However, if you remember the slide before, slide is coming. Each circle must be as large as possible. Can we make a larger circle than only this guy? We can. Let's take this guy. Whoop. Sorry, this was a 1, right? 1, okay. And let's make a larger circle. Huh. And now we realize that, hey, I have the case where C is 0. B can be both 0 and 1, so B doesn't play into this thing. So it is not A and not C. Now, this is optimized. It can't get any better. I mean, there's a theorem behind it. And it is cool because, you know, I'm not doing these theorems and like this and things. I'm just looking and drawing large circles. And I don't know about you, but for me, drawing large circles is a nice kind of thing. I'll come to that. Just give me a sec. And, you know, whatever the functionality is here, we can quickly do this thing and calculate it. Yes?
I don't understand why what we can answer. Why can't we in the second circle you drew? Why can't we do it one further to the right?
Like this.
Why can't we do that?
Very good point. Excellent. We have to go back. And we say the circles must span a power of 2. So it has to be 1, 2, 4, 8, 16 kind of things. Why? I mean, I can explain you why. It's actually quite simple. If I span 3, this is not sort of eliminating anything, right? But the powers of 2 actually cover because they are changing one after another. And you see that not A stays constant here, but here it changes to 1. So if I could take this thing, it would have been great. Now, there are some tricky ones. Who wants to see some tricky ones? Let's do a tricky one. Actually, let's do this. Let's not be lazy. And let me just forget this. Okay. Okay, let's take a funny, I'll only draw the ones, right? So that we can see. Let's, for example, take this and okay. Yes, sorry. You first let me make a mistake. Okay. Now, this one is quite funny because you can do a lot of number of things. The first one that you should realize, one of the cheatings that we do is, we can, I mean, you have to imagine that this guy wraps around. So I can actually take this guy with this guy. Whoa, cheat code activated. Okay, this is possible. Then you say, okay, it's not very great. I can do multiple things. They will both come to the same. So I can do this, and then I can either do this or do this. Let's do this. I like it. Why not? So what's the function? Anyone who wants to start? Let's try with this one. What do you say? Okay. Okay, so let's see. A is 0 here. Okay, so let's take a look. B is 0 here, B is 0 here. So this means that not B. And here, in both cases, C is 0, so not C. Right? So who wants to do the next one? Somewhere here? No? Yeah? A and B, right? These guys. That. Smart. And then there is this thing. This side. Yeah? B and C. This is C. And both B is here. So this is B and C. There you go. Simples. Okay. Too many things to press. Okay, now comes the more complex, sorry, question, yes.
How do we prove that
maybe the statement there was not very nice. We want to draw it as large as possible, because the larger the circle, the less we write. Okay? Does it make sense?
So how do we prove that it's the smallest, the smallest equation that we can write?
How can we prove? Good one. This is it. Sorry. This is the smallest sum of products. You can see that here already. You can take them into parentheses and simplify it further, right? But I'm telling you, this is the smallest sum of products you can write. Once you have the smallest sum of products you can write, you can still go and minimize it. That stands there. The other one is smallest you can write. It's usually pretty obvious from a simple fact that you can only do this for 3 or 4 variables. You can also do it for 5, which requires a little bit of imagination. I mean, I was curious at once and tried it. It's not very easy. I heard that you can also do it for 6 manually. Anything above 6, not a chance. I mean, then it's like a 4 or 5 dimensional. You have to think how they merge and match. But, you know, the most usual one is 3 and 4, and then you see it pretty clearly. I mean, the worst thing that you can have is a checkerboard pattern, right? So it goes 1, 0, 1, 0, 0, 1, 0, 1. And you say, hey, I cannot circle anything. And you immediately see it. It's like, hello, checkerboard. And then the best is obviously if everything is 1. That means that we didn't have to write any truth table, right? If all of them are this, which means that you can make one giant circle the size of the K-map. And then if half of them are 1, and you can make a nice circle and just cover half of it, you're saying, hey, I'm super stoked. Definitive proof is, yeah. Now, I've covered everything. I can write this, but it will be redundant. Because I have already every, you know, this one covers every possible case where the output is a 1. So if I cover this as well, like you're asking this one, right? If I do this as well, I'm adding another literal, I'm not changing the result. It's a redundant addition. But what you ask is correct. You could have also done this. I mean, instead of adding that guy, AB, we could have added this guy, right? Which is A, not C. Would have also worked. You can also add AB, but you are not, I mean, you know, you're just doing more work. It's just doing exactly the same thing. I lost half the class. Okay. Let's make this the fun one. And I'm supposed to do this on the blackboard, so give me a second. Oh, the other one is... No. People are already leaving. Okay, Frank, quick. So, I'm not drawing the entire table. I'm just drawing the K-map. This is why I need to keep the slides on. For those of you who are watching in July, you're missing very much. So, let's draw this table. I'm just replicating what's on the slide. Okay, now we have to assign the variables. Notice that, you know, if you're really the rebel type, like this corner was the rebel type, you can also play around with this. You're just making your life difficult. But this is AB, this is CD. And now you go and, you know, 0, 0, 0, 1, 1, 1. This is the important thing. Don't forget this. This transition here, 1, 1. 1, 0, the same here. 0, 0, 0, 1, 1, 1, once again, this transition, and 1, 0. Okay. Now, the first column is this AB00 is going to be, these guys right here. So it's actually 1, 0, 1, 1, you think, 1, 0, 1, 1. However, you have to be careful because this one is the fourth line, and this one is the third line. In this case, they are the same, so it doesn't really make any difference. Now, the second one here, A and B 0, 1, 0, 1, is this column here. So we are going, the first one is 0, the next one is X. We're going to talk about what X is, and then we have 1, 1. Unfortunately or fortunately, they are also not really blocking us. Now we have this part, 1, 0, 0, the 1, 0 part. Now this is here, be careful, right? The next 4, these guys will go into this column. Fortunately, they are all X's, or one of them is 1. They are X's. And then this guy, completely useless, all X's. Now, X means I don't care. Sorry. 1, 0, 7, 2 1. Sorry? There's another one, sorry. Will Frank manage the last 3 minutes without making a mistake? That was a narrow one. Okay. Now, X, we will come and talk and know about it, means I don't care. It can be a 0, it can be a 1. Do whatever you want. I mean, for the functionality, this means that probably this is never a case that's going to happen. So I don't care if your circuit generates a 0 or a 1. He's not generating an X. He's going to generate a 0 or a 1, and I'm free to do however I please. And since I want to have an easy life, I'm going to choose them as it fits my agenda. So if I'm going back, a don't care is circuit only if it helps minimize the equation. And boy, it will help minimize the equation here. So, what do you see? Which one shall I write? The bottom, look at that. Warrant. Well, this is great. It doesn't depend on AB at all, right? There's no dependence on AB. And Y equals to, so what is this? Who says C? Lost the middle there. Okay, C. Good. What else can I take?
The last 2 columns, so that will be just 8.
The last 2 columns, so this guy. Big blob. I like big blobs. Yeah, start whatever, hashtag Frank likes blobs. Okay, what else? There are more big blobs here. Yes?
All the corners.
Good one, good one. So I can take this guy with this guy and this guy and this. Yeah, good one. Exactly. So what does this give us? Who took it? You took it, right? What is it now? Which one? Yes? End of lecture? What do you say? So at this point, B0 B is 0. And so this is not B. And here we have not D, right? Okay. Before you leave, one last thing. What about this one? How do I circle this? That's a very good solution. However, it's an X, right? I'll just say this is a 0. So I won't take it. And I'll just say, assume that that guy is 0. So this ends up being my thing. So tomorrow we are going to continue and see some more of these tricks. And then we will move to doing these things more systematically.